Hello and welcome to the screencast for Chem Activity 36, Functional Groups, subtitled How Are Organic Molecules Classified? This is a screencast for Allied Health Chemistry at Missouri Southern State University, and I am Dr. Michael Garoot. This activity is not like the other activities. It doesn't really have a learning cycle in it. It's pretty much just some information and a set of rules, and then applying the rules. So it's more like a traditional practice worksheet. You've got some information up front, a list of rules, and then we're just going to practice working through these problems. So what I'm going to do is just kind of talk you through my thought process about functional groups and hit some of the highlights of things that I think you should pay attention to, that will be helpful for you to pay attention to. So I'm not going to read the entire information to you, but functional groups are a way of classifying organic molecules because it's convenient to know that when certain groups of bonded atoms occur, they tend to have the same kind of function, no matter if that molecule is large or small or what kind of molecule it is. And we're learning 20 or so functional groups. There are a countless number of functional groups. We're learning the absolute most basic set of them and some naming, just so that we kind of have some vocabulary to be able to talk about organic molecules when we move into the biological chemistry section of the class. So there is an organizational body called the International Union of Pure and Applied Chemistry. We call that IUPAC, that has come up with a list of rules for naming organic molecules that have different functional groups. And of course, some of those molecules, the names were in existence before this IUPAC was in existence. So some of the names are sort of grandfathered in, and we've already been exposed to that. For example, we've already learned how to name some alkanes. In Table 1 on this first page, and I hope you have your printed copy of the activity in front of you, but in our activity about alkanes, cycloalkanes, and alkyl halides, we learned the rules for naming alkanes and haloalkanes. And for example, we learned that the alkanes having 1 through 4 carbons are called methane, ethane, propane, and butane, and after that they follow a system: pentane for 5, hexane for 6, etc. When you start to follow a system, that's why we call them systematic rules. But some of the names are so old that they are just sort of grandfathered in. So methane, ethane, propane, butane are grandfathered in, and they become part of the system. There are often multiple correct ways to name molecules because there are these old-fashioned names. So like when we were learning inorganic nomenclature, and we learned that iron, if it has an oxidation state of 2, can be called the iron 2 cation, or it can be called the ferrous cation, and iron 3 can also be called ferric. The ferrous and the ferric are older names, not systematic, or at least not along the systematic IUPAC naming rules. So it would be good for us to know the systematic rules, and that way we have one good way of naming things. There are a few things that you just have to memorize, and there's no way around it. H2O is just water. There's no set of rules to name H2O as water. It's just water. NH3 is ammonia. There's no set of rules. You just have to memorize that it's ammonia. So there are a few things like that. And here's an example in this paragraph. The systematic name for formaldehyde is called methanal. Nobody calls it that. Everybody calls it formaldehyde because that name has been around forever. All right? So let me just explain how this table works. So we have the name of the functional group at first and a generic structure. So when I have a generic structure, when I see the letter R, I'm thinking that can usually be either, it's typically a carbon-containing group, is what it is. So some carbon-containing group. Think of it as an alkyl group if you like. Or you can just think of R as the rest, right? It's the rest of the molecule. Formally, R stands for radical. It's not important that you know what it stands for, but it just means R, the rest. So in this alkene, if I wanted to, I could put R's here. The idea is that an alkene has this unit in it somewhere, and that's a carbon-carbon double bond, and so you can see that in the examples here and here. All right, so let me give you an example. All of the rules that you've learned for naming alkanes, methane, ethane, propane, etc., those apply to all of these other functional groups. The only thing you have to do is, once you've identified the functional group, you get to change the suffix to something else. So, for example, if I have propane, which I can write in a condensed form like this, which I can also write in a stick structure like this. If I have a double bond in that, I can draw it like this. I can draw it like this. Let me make that a little closer. Okay. And I could even be more specific and draw out the whole Lewis structure. So C with 3 H's, a C double bonded to another carbon, like so. And that's why I made a mistake here. So that mistake that I just made there, if that was a 3, that carbon would have 5 bonds, right? 3 hydrogens and a double bond. That's not correct. So keep it at 2. This molecule has a double bond in it, so that makes this a different functional group than alkane. It makes it an alkene. And if I look at my table, then I look at the column that says base suffix. So all I need to do is find the base name, 3 carbons, 1, 2, 3. That would be propane. And then change the base suffix to ene. So I drop the ane part for alkane, and I add the ene part for alkene. So this becomes pentene. Oops. Propene. Pentene would be 5. Propene would be 3. So propane becomes propene. And that's my example. If I do the same thing for a triple bond, so that's difficult to draw in a stick structure, but in a condensed structure, it would look like this. It can be drawn in a stick, but it becomes a straight line because of its linear nature. And that has 3 carbons, 1, 2, 3, and that has a triple bond. And so the suffix for triple bond is YNE. And that's pronounced propine. So 2 things that I'd like you to notice that are very important. 1, spelling. Spelling is extremely important. I change the A to an E to a Y, and that changes the entire molecule. Propane, propene, and propine. The other thing that's important is pronunciation. So a Y, if you thought that sounded like an E sound, which it sometimes does in some words, it's not going to work here, because if you pronounce this propene, then it sounds like this. So you need to be careful with your spelling and with your pronunciation when you're doing nomenclature. And nomenclature is just a fancy word that means naming. So if I take alkanes, alkenes, alkynes, and I add one more functional group, which is aromatic. Aromatic is a pretty complicated functional group, but the most common aromatic is this structure, which is a 6-membered ring structure that has 3 double bonds. And that's really the only one that we're going to spend much time with. And that's called benzene. And if I put together alkanes, alkenes, alkynes, and aromatics, these are the only 4 functional groups that have only carbons and hydrogens. And so together, these are sometimes just referred to as the hydrocarbons. So the hydrocarbons are alkanes, alkenes, alkynes, and aromatics. Another nomenclature that I'd like you to pay attention to is these ones versus these 3. These ones are referred to as saturated hydrocarbons, and these 3 are all referred to as unsaturated hydrocarbons. The saturated versus unsaturated, you've probably heard that terminology with regards to fats in your diet, saturated fats versus unsaturated fats, and it means the same thing. In a saturated molecule, there is no more room to put any more hydrogens in it. So in this alkane example, there are no double bonds, and so you can't possibly get any more hydrogens on there. In an alkene, though, since you have a double bond, if you got rid of that double bond, you could put 2 more hydrogens in. And so anytime you have a double bond, a triple bond, or an aromatic, which looks like 3 double bonds, you have something that is unsaturated. That comes up in the questions at the end of this activity because it talks about a saturated group versus an unsaturated group. So anytime you see a double bond, that's considered to be a site of unsaturation. A triple bond is a site of unsaturation. Okay? So that's the difference between saturated and unsaturated. Haloalkanes don't get named as a base. So we learned how to name those too. So you just name them as prefixes. Now the prefixes are what we have when we have substituents. We also called those groups when we learned how to name alkanes, like for example, this one. So let's just do that one on my example page. If I draw that as a stick structure, it looks like this. If I draw it like this, then the rules that I used for that were find the longest continuous chain without backtracking. So I can go 1, 2, 3, or I can go 1, 2, 3. It doesn't make any difference. Whichever is 3, so that's propane. So if I pick these 3 for the propane. Then on the second one, I have a methyl, and so that's 2-methyl. And that should not have any space, right? So if I'm good about that, I keep it so there's no space there, and 2-methyl propane. So this methyl group, that's called a substituent, and we have rules for that. Whenever you name something as a substituent, you have to change its suffix. You changed it to a YL, so instead of methane, it becomes methyl, and then you put it out in the front. So that's indicated in my table by this column that says name when substituent, and the suffix becomes YL. So the methyl becomes the name when it's the substituent, and that goes out in front of the name. So when you're naming, you do the base name first, then you put all the substituents out in the front, alphabetize them, and give them numbers. So as you're looking through this table, pay attention to the examples and make sure that you understand how the examples illustrate how the rules are applied. In the case of an alkene, when you're numbering that, you need to include in the base chain that alkene. It has to actually include that. So if there's a branch, you're finding your main chain, the branch has to include the alkene. And then you also have to number it closest to that end. So I would number from this direction 1, 2, not from this direction 1, 2, 3. And then when I name that, I give it the number 2 because 2 is the first carbon where the alkene was found. When I look at this example, you might be wondering how that's 4-bromo. Well, it's cyclopentane, but since there's a double bond, you change the ending to ene, and then you have to number through the double bond as carbons number 1 and 2. On an alkene, on a cyclic, you could theoretically start at any place, but since the most important functional group that you're naming it on is an alkene, you've got to start with those being 1 and 2. And then that would be 3 and 4. And if I went the other direction, it would be 1, 2, 3, and 4. Whichever way you go, bromine gets number 4, and so that explains why that's 4-bromocyclopentene. One more time, on the alkyne, I have a 5-carbon chain, whichever way I go. So that's here. But then I don't count now closest to the branch. I count closest to the alkyne because that is the base name. So that means this has to be number 1, number 2, number 3, and number 4, and the methyl group is attached to number 4. So you see how I put those numbers then. 4-methyl, and then I have to specify where is the triple bond, so I need a number for that. If I'm completely honest with you, the systematic names are really a little more wacky than this. For trans-2-pentene, they might actually put it like this, trans-pent-2-ene, which tells you that the alkene is at carbon number 2. And this one, the same, would be 4-methyl-pent-2-ine. That is the formal, official way of doing it. It sounds awfully weird when you pronounce it that way. Most chemists won't say it that way, but it is the newest version of the naming rules. And so if you're forced to apply the pure systematic rules, then you'll do it this way. When you have an aromatic, you just find the benzene, and that's your base. That's your base name. However, what happens when you have a choice to make about the base? So my example here, let's make this a little simpler. Okay, let's compare this one and this one. These look very similar, and if you look at the functional groups, they're both aromatics. We have an alkane here, we have an alkane here. When we're looking for functional groups, we usually don't bother mentioning an alkane or alkyl group because pretty much every molecule has alkane or alkyl group. The most important functional group here is the aromatic. And when I'm numbering, so here's a tip. When you number, you have to either be in the ring or out of the ring, but you can't go like in and out of the ring together to make your longest chain. So for this one, I can do 6 in the ring, or I can do 1, 2, 3 outside of the ring. But I can't go 1, 2, and then go into the ring. That's not fair. So since I have 6 in the ring and 3 outside the ring, I'll pick 6 as my longest, and that's this aromatic, which we know is called benzene. And we see that right here as the base name. And then I need to name this part as a substituent. This part has 3 carbons, 1, 2, 3. 3 would be propane, but you change it, the ending to YL, so that's propyl. And it's connected to the middle carbon, the second carbon of the propane. So that actually makes it an isopropyl group. So this is called isopropyl benzene. That's a good name for this one. The other example is slightly different because I still have 6 in my chain here, but if I count out here, I have 1, 2, 3, 4, 5, 6, 7. 7 is longer than 6, so that's my longest chain, and 7 is heptane. So then I have to name the benzene as the substituent, and it is attached to number 2 of the heptane. And so when I look at the rules, when benzene is a substituent, it's not called benzene anymore, and it's not called benzyl, which you might think it would be called benzyl. It's actually called phenyl. So this is 2-phenyl heptane. Benzyl means actually something else. Benzyl actually means a benzene plus an extra carbon. So if I make a really long chain here, and then I put on it a CH2 and then a benzene, and this is 1, 2, 3, 4, 5, 6, 7, 8, 9, so that's nonane. And then this is a benzyl. 1, 2, 3, 4, 4 benzyl nonane. So that's tricky. Phenyl is the name for benzene as a substituent. Benzyl is the name for benzene with an extra carbon. So pay attention to that. That takes care of the important things on the first page. As we go to the second page, we start getting other elements in besides carbon, hydrogen, and halogens. So oxygen is pretty common. So let's do an example with alcohol. All right, so I'll page down a little bit. So when I have propane, if I have replaced one of the H's of the propane with an oxygen, turns out oxygen like to have 2 bonds, so it's going to be an OH group. And there are 2 ways I can do that. I can do it like this, or I can do it like this. So I tried it on the 3rd carbon, I tried it on the 2nd carbon, I tried it on the 1st carbon. Do you see that this and this are actually the same thing, just turned around? And here's how you can tell. I find my longest chain that includes the functional group. Okay, the functional group here says ROH. So it's the entire thing. So 3 is propane, but I drop the E and change the suffix to OL. So it's propanol. Same for this one. Propanol. And sure enough, this one too, because the main chain plus the OH, still 1, 2, 3, which is propane, and this is also propanol. So in order to distinguish them, I need a number. The number I use for this is the number of the carbon where the alcohol is, because that's the base name, has OL for alcohol. And I need to count closest to where that is. So when I count this one, it's 1 propanol, because I count 1, 2, 3. And when I count this one, I count 1, 2, 3, so that's also 1 propanol. But this one is 2 propanol. 1, 2, 3. We also call this one normal propanol, and sometimes you'll just put N-propanol, N for normal. And this one is also called isopropyl alcohol. The first name is the IUPAC, the systematic name. The second one is a common name or a trivial name because we know what an isopropyl group is. It's 3 carbons where something's connected to the middle one, and then you just say the word alcohol after it. Everyone knows isopropyl alcohol is the name for this, even though the official systematic name for it would be 2-propanol. It's good to know both. The next functional group in our list is phenol. Phenol is actually a molecule by itself. It's just called phenol. Phenol itself is the active ingredient in chloroseptic spray. So if you've ever used chloroseptic spray, you probably have an idea about what phenol smells like and tastes like. It is an antiseptic and a numbing agent, so people take it for sore throats. If you have a phenol, then you find that base part of it, which is the benzene plus the OH, and it's still aromatic, but it's no longer named as a benzene, it's named as a phenol, and so you have to find that and then what's outside of it. The carbon of the benzene with the OH gets number 1, and then you number around. 1, 2, 3, 4, 5, and 6, like so. A thiol. A thiol is like an alcohol, but the prefix thio means sulfur. So whenever you have a sulfur, it looks just like an OH group, except for the O is replaced with an S, a sulfur. So that's a thiol. These are also called mercaptans based on their substituent name. So if it's the base name, it's a thiol, and if it's a substituent, it's called mercapto. Mercapto also means sulfur. And then we get to the functional groups that contain carbon double bonded to an oxygen. Let me skip down to the bottom of the table at the little footnote. Several functional groups contain a carbonyl group. That's the carbon double bonded to an oxygen. That's not usually considered a functional group for naming purposes all by itself. We can recognize this as a carbonyl, but in order to name, we need to identify the functional group. And in order to do that, we need to see what's attached to the carbonyl. And starting from the bottom, I have acid anhydride, ester, amide, acid salt, carboxylic acid, ketone, aldehyde. So that's 7 different functional groups we're looking at that contain the carbonyl group. And so you have to look at what's on either side. So an aldehyde has a hydrogen on one side, at least. Ketones have hydrocarbons on both sides. Carboxylic acids have carbon on one side and an OH on the other side. You get the idea. You've got to pay attention to what's attached to it to know which functional group it is. So let's look at the examples for aldehyde. Methanol, we mentioned at the beginning. It's better known as formaldehyde. But how do I get that systematically? Well, it has 1 carbon. 1 carbon alkane would be called methane. Since it has the aldehyde functional group, change the suffix from ane to al, and we have methanal. Here's some that are good to get your mind wrapped around. Remember we said a benzyl group is a benzene plus an extra carbon. Here's sort of why that is. Here's a benzene plus an extra carbon. That's a benzyl group. Change the ending to aldehyde. This is actually a trivial name, benzaldehyde. But that is accepted into the IUPAC nomenclature. For an acid, we have benzoic acid. Again, it's a benzene plus a carbon. So that carries through. So for the aldehyde, what happens? So it's now time for us to look at combining functional groups. So when you have more than one functional group in a molecule, you have to pick the most important one to be the base name. So if I'm looking at this molecule, I notice it has a C double bonded to an O with an H, which makes it an aldehyde. It also has a chlorine, which makes it an alkyl halide or a haloalkane. I have to pick the most important one of those to name it, and there's kind of a rule of thumb for that, and that's also in my notes at the bottom. When you have two or more functional groups, choose the more important one to be the base name, and here's the rule of thumb. In general, the more carbon-oxygen bonds contained by a functional group, the higher its importance. So in this example, the aldehyde here contains an oxygen. The halogen isn't an oxygen, so it's less important. So I name this one based on the aldehyde. And as I apply the rules, I find my longest chain that contains the aldehyde, longest carbon chain. So that's here. That's propane. Then I change the ending to Al, so propanal. And then I name the substituent that's outside there, that's a chloro group, and I give it a number. And the number, 1 for the aldehyde carbon, and then 2, so that's a 2-chloropropanal. All right. Ketone is the next functional group. Notice that that ketone does not have a Y in it. So just Ketone, ketone. And I also pointed out some older name for this one. So if I go through the name for this ketone, following the rules, it's got a carbonyl group and it has carbons on both sides, so that makes it a ketone. Now I trace my longest chain without backtracking. I can go this way or the other way. I can go this way. If I go that way, whichever way I go, I have 4. 4 is butane, but change the ending to ONE. In this case, it's butanone. So you kind of just have to get a feeling for that. It's not butone. It's butanone. You just drop the E and add the ONE. Same for aldehyde. You just drop the E and add the Al. It's not like alkanes, alkenes, and alkynes where you drop the whole ANE and change it. And I don't have any good way to remember that except just practice. So there's my butane. It has a double bond in it, so it's butanone. And then I put a number for where the ketone is. Is it on carbon 1, 2, 3, or 4? So starting from this end, it's on number 2. So 2-butanone. And then carbon 3 has the methyl, so that's how you name this one. The older or trivial way of naming ketones is just to name the groups on either side. So on this side is a methyl group. On this side is an isopropyl group. You can call that methyl isopropyl ketone. And if you go to a factory where they get these kind of things as solvents in large barrels, they have a lot of ketones. They have a lot of MEK, which is methyl ethyl ketone. Well, that's this stuff without the methyl. Methyl ethyl ketone. But the formal name for that would be 2-butanone. So you kind of have to know both names if you're working in a place like that. Let's go on to carboxylic acid. So carboxylic acid has the carbonyl group attached to an OH, and then an R group. So this one is the simplest one would be where this R is just hydrogen. And so if I were naming that one, it has 1 carbon, that's methane, drop the E and add OIC, so that would be methane oic acid, methanoic acid. Nobody calls it that. They just call it formic acid. Just like for the aldehyde, we have formaldehyde with the 1 carbon. We have formic acid. So you kind of have to know that one. The next most simple carboxylic acid is this one. And this is so common. You just have to know both names for this, and you have to know its structure. So it's 2 carbons. The carbonyl with the OH, that's my carboxylic acid. So I find my longest carbon chain that contains that. There's 2 carbons. So that would be ethane. Change the ending to OIC, then add the word acid, so ethanoic acid. But this is our old friend, acetic acid. It's the acid that's in vinegar. It's the one that when we learned how to draw the structure for it, we drew, or the formula for it, we drew it like this, HC2H3O2, right? And then we drew the ion for that, C2H3O2 minus. And that's acetate. Check it out. Acetic acid, which does have this formula, it has the 1H written in the front so that we know that's the acidic one. That turns out to be this hydrogen. The acidic hydrogen is the one that's attached to the oxygen. And when that one goes away and it becomes the conjugate base, it becomes acetate, C2H3O2 minus, but check out the structure of acetate, which is in my next functional group. It's this. And count it up. CH3CO2 minus. Well, that's the same as this. So at this point, we know the actual structure of acetic acid and acetate, not just the formula. So when you see, so you just, it's going to come up a lot. What's the structure of acetic acid? You should know it. CH3, C double bond O, OH. And there are other ways for abbreviating this. You'll also see it written CH3, COOH, CH3, CO2H. And these are both abbreviations for carboxylic acids. These would be the condensed structures. So I'm only drawing the sort of somewhat condensed, but if you really, really condense it so that you don't have any bonds, you're just showing it like in the old days when you'd have to do this on a typewriter and you have to write it in one line. CH3COOH means this, and you just have to know that. CH3CO2H means the same thing, and you have to know it. This one we could write CH3CO2 minus or CH3COO minus, and that would mean the same as this. So practice getting those things into your memory about carboxylic acids. Okay, if I have a carboxylic acid, notice that in that functional group there are 3 carbon-oxygen bonds. So a carboxylic acid is a more important functional group than, for example, an alcohol, which has only 1 carbon-oxygen bond. And so if I make up an example for that, so here's an example. I've got 1, 2, 3 carbons, so that's got to be a, well, let's give myself some more room there. That's got to be a propane. But what's the main functional group? Because I have 2. This is just an OH group, so that's an alcohol. This one is a carboxylic acid. According to my rules, this one is more important. So my base name is going to have to include the carboxylic acid, but not the alcohol, because I can only include 1. So it's going to be propanoic acid. And that does have a space. And so then I can't name it as an alcohol because I've already named it as an acid. So I go to my rules for alcohols. And I have to put that out in the front as a substituent, and so now I have to call that a hydroxy group. So that group is hydroxy. And I need a number. So the number would be starting with the most important one, which is the propanoic acid, making that one number 1, this one 2, and this one 3. So it's 3-hydroxypropanoic acid. And in my example here, I have a 2-hydroxypropanoic acid. If I had what if I have an extra functional group there? This one isn't actually on the sheet, but I thought I would mention it anyway. Here's my carboxylic acid again. It's got my C double bond O with the OH. But here I have a C double bond O that has carbons on both sides. So what's the functional group that has carbons on both sides? That's this one, right? Ketone. So here I have both a carboxylic acid and a ketone. Well, the carboxylic acid is more important because it has 3 carbon-oxygen bonds, and I have 1, 2, 3 carbons. So again, that's propanoic acid. And that takes care of everything except for this ketone. And here, oh no, my table doesn't say what I do for a ketone when it's a substituent, but I'm just going to tell you. It's called oxo. And that actually works for aldehyde too. It's also called oxo. So I would actually call this one 2-oxopropanoic acid. But there's a common name for that too. The common name would be keto. The common name for this would be beta-ketopropanoic acid. And in a later activity, we'll learn why it's beta, but, oh, and that's wrong. It would be alpha-ketopropanoic acid. And later on, we'll learn why it's called alpha. This isn't, you don't have to know this one, but I've just got a little carried away with things that we're going to see later in the class. And so I went ahead and obviously I like this stuff, so we're 42 minutes into this activity, which isn't even an activity, and I just can't shut up. So I guess it's time for me to be quiet. I will mention that in Table 2, these last few functional groups are more along the lines of the common naming rules. Some of these have systematic rules, but they're really challenging. I'll give you an example of the one that's the least challenging. So this is an ether. It's got an oxygen in the middle of 2 carbon-containing groups. If I just say ether, if that brings anything to mind, like something you've ever heard about or you've smelled, it's this one. The standard ether that you're probably familiar with is diethyl ether. So if people just say ether, this is the one that they mean. So notice that the naming rules here are kind of cumbersome. You just name each of the R groups, and then you just say the word ether. But in this case, you don't want to call it ethyl ether. That sounds weird, so you call it diethyl ether. If I were to name this systematically, which I don't have the rules for that here, but if I were going to name it systematically, I only have 2 carbons in my base chain, because then I have an oxygen. So my base chain is just 2 carbons, so that's ethane. And then I have this group, which is an ethane with an oxygen, and this may make sense to you. This is called ethoxy. So the actual systematic name of this is ethoxyethane. It sounds kind of weird, but that's true. Here you have a benzene, and this would be a methoxy group, so you could call that methoxybenzene. But if I just apply these rules, which I think are simpler, you just find the things on either side of the oxygen, and you name each of the groups. So I have a methyl group, I have a phenyl group, and I put methyl before phenyl because M comes before P in the alphabet. All right? So you get to the exercises. The answers for these are given in the exercise solutions. I suggest, well, the first one is sort of walking you through how do you identify functional groups. So you're going to write the name of the functional group that fits this description, then look at the answer, and then pat yourself on the back if it's right, and if it's wrong, try to figure out what it is that you missed. In number 2, you're just going to list the functional groups. Alkane is kind of a given, so you don't have to say alkane. So you're going to list all the functional groups. And I'll give you a hint for that one. Let's see. I'm counting in my head. I'm going to say there's 9 functional groups in the 7 molecules. So 2 of them have 2 functional groups and the other ones only have 1. So you'll list them all. And then number 3 says you go back to those and you go ahead and give them names. So you're going to look back at the naming rules and you're going to give them some names. And you can write them here. Then it goes the other direction as well. So if I give you some names, then you can draw structures for those. And finally, list the functional groups for the ones that you just drew. So this is a nomenclature activity. You draw the structure given the name, or you give the name if the structure is provided. So now that we're to the end of this activity, we're also to the end of the activities for quiz number 5. So quiz number 5 includes the activities beginning with pH and ending in these 4 activities having to do with organic functional groups and naming and isomers. So you might be thinking to yourself, wow, this is a lot of stuff. When I have this class face-to-face, when I get to this point of the class, I typically allow students on the exam to bring in a note card. And so I'm going to allow you to do that as well. I'm going to allow you to have a 4x6 note card. And on that note card, you can write whatever you want, but it needs to be things that you've written on it in your own handwriting, not printed out from the activities and, reduced down in size with a photocopy machine or anything like that. It has to be stuff you've written in your own handwriting, and it's going to be a 4x6 card. So I'll put that in writing right here. For quiz number 5, you may have 1 4 inches by 6 inches note card written on one side only, not both sides. There's a reason for that, because I'm going to have you keep that card and add to it perhaps in the future. So 1 note card, 4x6, written on one side in your own handwriting. And you can use that on the quiz, in addition to the typical exam cover sheet that you always get to use. So that's this guy that has the constants and the solubility rules and things like that we probably won't be needing so much on the organic chemistry part. The periodic table is always useful, so that's always helpful. But in addition to that, you can have 1 4x6 card. Now, if you don't have a 4x6 card, that's fine. You probably have a ruler. Just cut out a piece of paper to the size of 4 inches by 6 inches, and you can write on it. And when you take the quiz, I will ask you, and then at the end of the quiz, you will submit your 3 essay questions on your own paper, and then you'll take a picture of those 3 essay questions, and what I will ask you to do is lay your note card right there, so that when you take a picture of your 3 essay questions, you also include your note card in that picture, and then you submit that with your quiz. As we're thinking ahead in the future, you'll probably get to add to that note card for quiz 6 and quiz 7. So you'll be able to write some more things onto it as you go forward. So if you don't use up all of the one side, you'll have more space to use for the last 2 quizzes. When we get to the final, you will not get to use your note card on the final. The final is going to be only multiple choice, and it's going to be testing just what you know without any extra notes and things like that. So I will let you have your note card on quizzes 5, 6, and 7, but not for the final, just so you know. So this completes the screencast for Chem Activity 36 and also the material for quiz number 5. Check your answers for Activity 36 on the exercise solutions on Blackboard, and you'll be ready for the quiz. Then we only have 2 more quizzes to go. Cheers!